Good morning, afternoon, or evening. Welcome to today's panel discussion on quantum science and technology. I'm Colonel Randy Pugh, the Senior Marine at the Naval Postgraduate School and the Deputy Director of the Naval Warfare Studies Institute. On behalf of the President of the NPS, Admiral Anne Rondeau, I would like to first sincerely thank today's panel members, our moderator, and most of all, our Navy and Marine Corps senior leaders dialed in today for your participation in our discussion. Thank you for the generosity of your time. Today's panel is on quantum science and technology and its implications for the DoD, a subject of vital importance in this new era of great power competition. Knowledge of this emerging technology, which is certain to become increasingly part of emerging capabilities, is critical so that we can not only guide the development of these new capabilities for future warfare, but also so that we can ensure our warfighters are prepared to integrate them and leverage them in combat. Today's event is part of a 3-event series. The first event was a presentation 2 weeks ago, Secretary of the Navy guest lecture by Nobel laureate Bill Phillips. That was followed by last week's roundtable discussion on atomic clocks and quantum sensing. Today's event will be on quantum computing. We hope this series of presentations will help demystify quantum for you. We hope that it will help you to understand the tremendous implications quantum S&T holds for the Department of Defense, to prevent strategic surprise, and to create strategic surprise. We hope our panelists will help you to separate fact from fiction. They are all anxious to answer your questions and to engage with you in a discussion about where we are and where we need to go with regard to quantum research. War is the ultimate learning competition, and NPS is perfectly positioned to support the Department of Defense along all 3 axes: enhancing the intellectual capital of our military and civilian professionals, exploring new operational concepts, and helping to develop the capabilities needed to realize these concepts. To support this mission, NPS has created the Naval Warfare Studies Institute and this Emerging Technology Series for Naval Leaders. I want to ask Dr. Sheila Vaidya to introduce our topic, our moderator, and our panelists. Sheila supports the Marine Corps' Deputy Commandant for Information, and here at NPS leads NWSI's Emerging Technologies branch. Sheila brings her own expertise to this subject with a distinguished career at AT&T Bell Labs, as the ISR lead at Lawrence Livermore National Labs, as well as other significant experiences working in Silicon Valley. Over to you, Sheila.
Thank you, Randy. Greetings and welcome once again to Seapower Conversations panel discussion on quantum information sciences, specifically on quantum computing today. Co-sponsored by NPS's Center for Executive Education and NWSI. Few words about NWSI before we get started. The Naval Warfare Studies Institute is a new organization formulated to align interdisciplinary research and education within NPS with Navy and Marine Corps priorities. By strengthening warfare concept and capability development while simultaneously enriching the intellectual capital of students to outthink, outmaneuver, and outfight. It's a gateway between naval forces, warfare centers, acquisition commands, the naval education enterprise, industry, academia, and NPS senior leaders, faculty, and students. We're defining solutions to future warfighting challenges, revamping defense business practices, and prototyping emerging technologies. To accomplish this charter, NWSI is built up of multiple interconnecting blocks: emerging technologies, critical thinking, warfare domains and disciplines, wargaming, and warfighting concepts. The Emerging Technologies branch scouts out new and revolutionary technologies with critical warfighting implications, brings relevant experts to the table for group interactions, such as our panel today, and facilitates follow-on relationship development. So now to the topic of the day. So why QIS? Because quantum information science and technology holds incredible potential for US economic growth, technology advancement, and national security. In a nutshell, quantum sciences uses the properties of nature at the smallest scale to create meaningful technologies. Super sensitive sensors and precision timing can aid navigation, especially in a GPS-denied arena, help find things underground, ensure that our energy grid is secure, and much more. Quantum computing can help discover new drugs and really secure communication channels which we rely upon for all our financial transactions as well as national defense. So is a quantum computer just a souped up classical computer? No, it's not. They're really two complementary beasts, each with its own strengths. Traditional computers are great at data crunching, email, spreadsheets, desktop publishing. They excel at storing data, whereas the very same quantum state fragility that makes for a good sensor creates challenges when building a quantum computer. Quantum memory barely lasts a few microseconds at best. On the other hand, a quantum computer can run specific algorithms much faster, solve certain classes of classically intractable optimization problems encountered in military logistics and resource allocation. And the threat of quantum computing is that it may crack many of today's encryption techniques and replace them even with those which are truly impossible to hack. So to tell us more what's here and now versus the longer term and assess the competitive landscape in quantum computing, we've assembled a team of leading experts today from government and industry, Dr. Charlie Tahan, Dr. Bob Wisnieff, and Dr. Krysta Sabor from Microsoft. Unfortunately, Dr. Scott Aaronson could not join us today. So a few words of introduction. Dr. Charles Tahan is the Assistant Director for QIS and the Director of the National Quantum Coordination Office within the White House OSTP, which ensures the coordination of the National Quantum Initiative and QIS activities across the federal government, industry, and academia. He's on detail from the Lab for Physical Sciences, where he still serves as their chief scientist and head of their intramural QIS research programs. Previously, he served as technical director at LPS, leading efforts in computing, communication, and sensing from novel device physics to high-performance computing architectures. His contributions have been recognized worldwide. He is Fellow of the American Physical Society and ODNI S&T Fellow. With a PhD in physics from University of Wisconsin, he was an NSF postdoc at Cambridge, Center for Quantum Computing in Australia, and the University of Tokyo in Japan. He also served as Chief QIST consultant within DARPA's NTO office prior to his distinguished career at LPS. We are indeed honored to have Dr. Tahan with us today. Bob Wisnieff joined IBM in 1986 with a PhD in applied physics, pursuing research in flat panel displays in his early years. He is currently the CTO for their quantum computing program and a member of DoD's Defense Science Board. Prior to this position, he managed the quantum computing simulations and application group, following stints managing their microelectronics lab and interconnect technology and advanced display lab. We look forward to your perspective, Bob. And finally, we have Dr. Christa Sabor, General Manager of Quantum Systems at Microsoft, where she leads the team to realize a commercial-scale quantum computing ecosystem. She spent her early years at Microsoft developing machine learning methods for web applications. With a PhD in computer science from Columbia, Dr. Svore was named one of the 39 most powerful women engineers by Business Insider in 2018. Dr. Sabor serves as DOE's Advanced Scientific Computing Advisory Committee, DARPA's ISAT Committee, as well as on the National Quantum Initiative Advisory Committee. She's received several awards and accolades along the way, and we are eager to hear from you, including about Microsoft's recent announcement on Azure Quantum. Welcome, Christa. The panel will be moderated by Dr. Paul Lopata and supported by Commander Mike Maniccia from NPS. Dr. Lopata is an internationally recognized luminary in QIS and cybersecurity. He is currently the Principal Director for Quantum Sciences in the Office of the Undersecretary of Defense for Research and Engineering, where he leads the Defense Department's effort in quantum science technology modernization. Previously, Dr. Lopata served as the Associate Director for Cyber Technologies, where he steered the evolution of the Federal Cyber Strategy and coordinated cyber research DoD-wide, as well as with international partners. With a PhD in mathematical physics from the University of Illinois, Dr. Lopata's early career included consulting for DARPA and IARPA, working at ARL, and researching quantum technologies at LPS. We are truly honored to have Dr. Lopata with us today, moderating our panel. Our POC for Quantum Information Sciences is Dr. Frank Narducci, Professor of Physics at NPS. Frank joined NPS in 2017, where he oversees their QIS portfolio in parallel with his research. Unfortunately, Frank is out sick today, so we will not be hearing from him. And with that long introduction to our luminaries, over to you, Dr. Lopata. Lead us off.
Thank you, Dr. Vaidya. I'm really looking forward to the discussion today. We have some great panelists, and I want to thank you, Dr. Vaidya. Thank you, Colonel Pugh, for the opportunity today. I think this is a fantastic chance to talk with the folks at Naval Postgraduate School, talk with the flag officers, general officers in the Navy and in the Marine Corps, and everyone else who is here to understand how quantum computing is going to make an impact on the Navy and the Marine Corps, and some of the recent things we're expecting to see in coming years. And before my role today really is to let you all hear from the moderators, or from the panelists rather. I'm the moderator, but as the moderator, I think I should give a little bit of an introduction before handing it off to the panelists, and maybe try to answer the question, why should the Navy and the Marines and the rest of the DoD care about quantum computing today? What makes it such a big deal? Why is it a hot topic of major publications? A national initiative you heard about that Dr. Tahan is helping shepherd in the White House Office of OSTP, and it even came up several times during Senate confirmation hearings of the new Secretary of Defense and the new Undersecretary of Defense. And so what makes it such a big deal, and what should we look for support of the Navy, Marines, and broader DoD? And in order to answer that, I'd like to step back for a second and take a moment and really reflect upon what computing generally does for us, for a 21st century military. I would argue that our ability to, as a nation, to build, maintain, and to take advantage of our military strongly depends upon our ability to take advantage of computing. Now, one might argue, okay, maybe that's not true. Maybe it's the nuclear triad and strategic deterrence which give us might, or maybe it's various aspects of force multiplication and precision fires that we take advantage. Maybe it's ISR and the signals that we can take in and understand the complex battlefield that gives us an advantage. Or maybe it's our command and control that gives us a distinct advantage over adversaries. But I would argue, if you look under the hood of each of those that I brought up, and many other things that serve as major functions in the DoD, that they're all enabled by computing somewhere in their life cycle, either in their design stages, like the way that DOE supports our nuclear triad through major compute power, whether it's precision fires and how the GPS system and all that's involved there involves a tremendous amount of computing, both for its design, its maintenance, and running. Whether it's our signals, ISR, those really depend upon getting the signals is one thing, but being able to make sense of them requires a whole lot of compute all the way down the line. And so when we look at, as a nation, things that give us a great advantage for our military, computing is right up there. And the fact that 20th century computing, through our academic lead, through our industry lead, and into the 21st century, our computing lead, really gives major strength to our military. And in some ways, quantum computing and the journey into that is just a new step in that direction. Understanding that in order to maintain our might in the 21st century, we need to maintain our lead in compute. And so in our discussion today, I think we'll get into a lot of details of historically how we got here, and some of the things that we're currently taking advantage of through government initiatives, through industry efforts, through academic efforts. And I think keeping in mind that throughout the life cycle of our acquisition, throughout how we fight, is really reliant upon compute in many ways, and taking advantage of this new capabilities, these new quantum computing capabilities, are going to be key to maintaining an advantage in the 21st century. And so for the discussion today, I have a whole list of questions that I have ready to give out to our panelists, and I think I'm ready to do that. But I also want to be mindful that I know a lot of audience members have a lot of questions you're coming with, and I'm sure you'll think of questions as we go on. So I would encourage you to send those questions in. We have a Q&A that we're ready to go with, and I'm eager to take advantage of the questions that you all have, and as I'm leading this discussion. But to kick us off, I'd like to give each of our panel members a few minutes to introduce themselves, talk about their key interests, what some of their focus is for where they work, and what they're looking for towards the future. It's a little bit open-ended, but I want to hand it over to Dr. Tahan first, and ask him, as you're working in the White House Office of Science and Technology Policy, how are you looking at this problem of quantum computing, and what are some of the things you're thinking of, maybe in 5 or 10 minutes. Over.
Well, I don't know how I can compete with that introduction. That was maybe the most amazing introduction I've ever gotten. So thank you to the organizers for that. I'll just say a little bit about what's going on in the Office of Science and Technology Policy. One of our jobs is to work with all the agencies to create a strategic plan for the National Quantum Initiative broadly. And quantum computing is clearly a big part of that. There's a lot of commercial interest. There's a lot of investment from really all across the government into the research and development of this. When I think about what we care about in the next few years, first and foremost is how can this technology benefit society over the next decade, and where do we want to be at the halfway point of the National Quantum Initiative in 4 years? Have we found applications in the near term that could drive further investment? Do we clearly understand the resource requirements for the longer term applications? And then all the things around that, how do you enable the nascent industry to move fast? What's the supply chain that needs to be put in place to ensure that the U.S. benefits from this new technology? And how do we protect it? Both in our research environments and our companies, how do we bring cybersecurity and research security up to the level to protect this new technology as we invest a lot of money in trying to make it a reality? And they're not trivial questions, because quantum computing is a very unique domain. I think the last thing is, what are the societal implications of this technology, and can we make sure that as it grows, it benefits all of the people of this country? On one side, just providing new types of technology they can buy and use. On the other side, how do we train people to participate in this economic growth, to actually contribute to it and benefit that way? So that's some of the things we care about. Look forward to the conversation today. You're on mute, Paul.
Of course I am. Thank you, Charlie. Next, I'd like to hand it over to Bob Wisnieff, Dr. Bob Wisnieff from IBM. There's certainly other two panelists are from industry, and certainly have a different job jar every day on it. But I think there's real complementary views on the technology and things we're looking towards for the future. So perhaps Dr. Wisnieff, maybe tell us some of the things you think about when you're thinking about quantum computing, and some of the major things that you focus on at IBM. Over.
Okay, thanks, Paul. Yeah, I think the view within IBM of quantum computing is forming a new triad of computing for the future. One in which we have the conventional supercomputers, which we try to achieve the highest possible performance on, married to the latest AI accelerators, in order to use AI to accelerate different classes of problems which are not tenable for classical compute. And then finally, for some classes of problems, to use quantum computers in order to accelerate solution within there. So we've been looking at all three areas intensely for the last decade or more within IBM. Within quantum computing, probably the least mature of the three, a lot of the focus for the previous 10 years has been trying to find a qubit platform that we could base small machines on. And about 5 years ago, getting to the point where we could build very small 5-qubit machines and put them on the web for people to experience how a quantum computer works. And increasingly now focusing on not only how do we make the qubits better, because we have to get better qubits if we're going to make machines that can solve problems that matter, but beginning to think about the entire hierarchy of architecture that will enable that to actually be applied to problems that people care about. And that runs the full gamut from the control electronics, the cryostats, the compilers. How do you optimize these machines in real time? How do you make them consumable by people whose expertise is not in quantum computing, but in AI or in chemistry or in optimization or in any other fields? And in the end, it is that consumability of a new resource that allows it to be truly taken advantage of. Back to you, Paul.
Thanks, Bob. Had to check I was off mute. So, our final panelist is Dr. Christa Sabor from Microsoft. Maybe over to you. Maybe an introduction to some of the work that you work on and how you view the field. Over.
Thank you. It's a pleasure to be here today to share what we're doing at Microsoft, but also to share how the community, the field is evolving and what areas we can have impact in together around quantum computing. When we think about the promise of quantum computing, I think just as we've heard from the other two panelists, right, the key application areas are really in chemistry, cryptanalysis, and materials science. With potential to have impact in machine learning and artificial intelligence spaces over time. But the reality is for these application areas, we need a very large quantum computer. And so both Charlie and Bob mentioned, we continue to need to build up the system, right? The capabilities of that system to enable solving such applications in chemistry, as an example. One of the most promising application areas for a quantum computer is in computational catalysis. So the ability to study how a catalyst and then, create, for example, or learn how to design a catalyst that will enable a more efficient reaction rate, whether that be in carbon fixation to help combat global warming, or whether that be, say, with nitrogen fixation, where we want to improve industrial fertilizer production. So computational catalysis is a wonderful application area for quantum computing. Quantum computers are good at big compute, but not big data. And so that's where we really do need to be able to scale to a large industrial scale quantum computer in order to see that full promise of quantum computing come forward. I think as we think about quantum computers, it's also important to realize that quantum computers do not operate in isolation. It's hybrid. Quantum computers are hybrid in their internal representations, right? How we write a program, it's controlled by classical compute, and the applications themselves are very hybrid. You have intense feedback between a classical system and a quantum system. And so when we think about deploying quantum solutions, we really need to deploy those in concert with, right, aligned with classical compute, as Bob mentioned, right, aligned with a supercomputer. How do we operate this together? A quantum computer is an accelerator, much like you think about a GPU, right? So when you think about programming a quantum computer, it's very much like the framework you would use to program a GPU. So when we, given that we don't want to operate in isolation, this is where the power of the cloud really does come in, right? The quantum computer can be deployed in the cloud as an accelerator, as a member of that heterogeneous compute environment. And so with that, in order to bring these solutions forward and to also innovate around new applications over time, we also need to improve and provide access to tools, to a platform, to an ecosystem, to the devices themselves. And this is where, as Sheila mentioned earlier, we've just announced, for example, Azure Quantum, which is an open ecosystem for quantum computing and quantum impact, where you can come today to write a quantum program, deploy it on quantum hardware, and begin innovating for this quantum future. But I also want to emphasize that quantum computing and the impact of quantum computing is actually already, now. It's right now. You can run on quantum computers now. And what we've learned from designing applications for quantum computers is that some of these methods we can emulate classically. And what that means is in, for example, the space of optimization, we can take what we've learned from studying from decades of quantum research. We can take some of those learnings, apply them to classical algorithms, and run those solutions on classical hardware today to achieve speedups. And I think these areas, these application areas are very important or would be very important to all of you. The impact here is in optimization, which covers everything from scheduling to logistics to risk analysis and mitigation techniques. You look across, across the space of optimization, and there, it really is pervasive across industries and applications. And with quantum-inspired optimization solutions, we can give already improvements on state-of-the-art solutions. So it's very exciting to see the impacts of quantum computing come through not only in, as we scale up to the full promise, but also through systems and solutions that we've been able to develop as we've learned about quantum computing. I think when we think about our national capabilities, we continue to need to strengthen our capabilities in order to realize industrial, full-scale, high-impact quantum computing, right? Valuable solutions. We need to strengthen our capabilities in the ability to develop, manufacture, and deploy an industrial quantum machine. We need to continue to look at the supply chain. How do we facilitate the supply chain? Do we have enough people understanding materials science and materials design, cryogenics, right? The necessary infrastructure. We need to invest in our workforce, the workforce that not only looks at the application side, but also all the way down that hardware, the hardware chain, right? All the way down to people knowing how to build machinery that will enable, sub-nanometer precisions on line edge. So we need all of these advances in order to bring quantum computing forward. And then, as I mentioned earlier, we need to then provide also access to tools, to an ecosystem, to platforms, so that we can continue to innovate on the application spaces as well. So I'm really excited to hear your questions today and to have this great discussion around this revolutionary and disruptive technology together.
Thanks, Krista. Yeah, so I'm going to kick off some questions. We already have a few in the Q&A. I'll encourage everybody out there to contribute your own questions. I'm sure things come up while we're talking. Maybe you're asking yourself, why are they referring to the classics? Why have Plato and Socrates come up? And where does this distinction between classical and quantum, and where other things? So certainly ask your questions. We'll look forward to them. To kick us off, maybe I'll send something over to Dr. Wisnieff. In terms of senior Navy and Marine Corps leaders, whether they're civilian and or military, What are the key things they need to know about quantum computing today? Are there things that you would say they would be, is it in the R&D space? Is it in the operation space? What are some key things they need to know for, either decisions they'll see or influence they can have? Over.
Okay, thanks, Paul. So I think one way to sort of scale where we are in quantum computing is to place it in context of things like supercomputer development over the last 20 years. So if you look at the advances that were made under the DOE ASCII program, a lot of that was the DOE setting up thresholds that they wanted to achieve, which caused an ecosystem of providers in the commercial space to develop new technologies. And initially, the small demonstrations would cost tens of millions of dollars to $100 million to do. But by the time you're getting to full deployable systems, you're talking about a billion or billions of dollars of investment to get to a fully qualified system. And that is something that takes such a pull from an application space that the government plays a pivotal role in making sure that the focus is given in the right areas. So if I draw from the ASCII program and similar programs that have happened over the last decades, I think right now we're in that early R&D. We're in the tens of millions of dollars of investment to get to systems that perform today, and we're getting to systems that clearly demonstrate that the rules of quantum mechanics are at play in the systems we can build. But these systems still have demerits that prevent them from fully cashing in on the promise that we want to get to. We talk a lot about something called fidelity. When we do something with our system, what is the probability that that system is going to do what we ask it to do? And today we're around 99%, and we can probably push the systems by building better qubits and better control electronics up another order of magnitude or so, but we rapidly hit a wall there, and we'll begin to then do things called error correction on top of those qubits. And every time we add layers of control, we're adding layers of complexity to the way the machine has to be designed, built, and run. And those machines will cost now hundreds of millions of dollars to bring to the fore. And those machines will begin to now get to the point, as Christa pointed out, to be large enough to solve problems that can begin to matter. And we're talking about hundreds of thousands of qubits or more in those machines over time. And now, much like a conventional computing system, all of that complexity that lies within the computing system has to somehow be managed so that the end user who's trying to solve a problem in chemistry doesn't have to worry about error correction, doesn't have to worry about the details of the compiler, doesn't have to worry about how the qubits actually work. Just focus on solving the problem that's important to them. And so it's getting up that stack, getting to the point where we have the full software stack is something that we can begin to experiment with today's machines. We can see what the art of the possible is to begin to see which areas like chemistry, like optimization, and which areas of chemistry might be most important for us, and which areas might be further out, so that we can scale which problems are going to be the first for us to touch, and what it will take to do that. So to me, that's the beauty of where we are. But we face in technology this rule of thumb that to go from research to development to manufacturing, each one of those is about an order of magnitude more investment. And so we're facing some gigantic investments to take this fully over the finish line to real solutions. And it's one where that entire stack that I think Microsoft is working on, IBM is working on, and we're working with a lot of other companies and universities around the world in order to see what can we do and where are the issues, what are the options in order to architect those machines to do something that is useful, and then which are the first applications that we can touch to gain that utility. Paul.
Thanks, Paul. The next question we have is for Dr. Tahan. How did we get here? Was this a result of strictly academic work? Is this just industry work? Was it pushed along by government policy, by government investment? The fact that 40 years ago nobody was talking about quantum computing. Now it's easy to find information about it. Lots of headlines on the topic. So could you give us a sense for how we get here?
Sure. Thanks, Paul. I want to try to weave in some answers to some of these questions too that I'm seeing. I think the first thing to know, everybody should know on the phone, is that quantum computers today won't be integrated with battlefield ops anytime soon. We have, after 20, God, we're getting old, right? Me and Paul started in this career maybe 2000. After 20 years, 25 years of sustained investment in devices, can you make quantum bits, analogous to a transistor? We now can, and we can do more than that. Companies and big labs can integrate tens of qubits, 50 to 100 qubits together, have them function as a quantum computer to see if quantum computing kind of works and to do research on. And that took a long, sustained investment, mostly from the government, Department of Defense, intelligence community, National Science Foundation, etc. In addition to some, company investment, going back that far as well. IBM is an example, Microsoft is an example. Sustained long-term investment just to get where we are today. And we're in this new phase where we're hoping to get to that next phase of integrating and towards a large-scale quantum computer. And in that, we have applications. And quantum, I like to say that quantum computing is not a particle detector. It's not a gravity wave detector or a telescope. It's not a pure science experiment. There are clear economic and national security implications of this technology. So we do have to, to answer one of the questions I'm seeing in this chat, we do have to protect it. The first killer app that motivated a lot of the research funding in quantum computing was Peter Shore's algorithm for factoring numbers, which, if implemented on a very large quantum computer, could break public key RSA encryption. So one of the things we're doing to protect it as a nation and as an industry, is to deploy and work towards deploying cryptographic protocols that are resilient to future quantum computers. That's one way that the nation can protect itself and the industry can protect itself. But we also have to think about the research security of it. How do we do research? And here, how do we do research where our intellectual property is not stolen or lost? And here, the government and industry is also very well aligned. After all this investment, we don't want that to go away overnight, right? We want to be able to take advantage of it for the good of the nation. Does that get to some of what you're asking, Paul? Was there something else you wanted me to? Sure.
Yeah, that was some good background information. I think putting the sort of scale of it in context and some of the timelines is important to understand. Dr. Sabor, I think I'll ask the next question of you. You mentioned one of these things about how things, systems and solutions are being realized today that take advantage of this new understanding we're developing for quantum computing, and even some of the new tools we're developing for quantum computing that in some ways has spin-offs for industry, for other things today. Could you provide us a little more detail on that, and maybe how we could think about it in terms of spin-offs for perhaps the military as well?
Of course. Yeah, so as we've studied quantum algorithms, actually I should start with, one of the reasons we built out such an incredible team in the quantum algorithm space was because while we had, mathematical proof that a quantum algorithm should provide a speed up, we didn't understand how those speed ups would translate when you implement it on hardware. And so when you think about a quantum algorithm, it's absolutely beautiful, right? It's absolutely beautiful to see that we have speedups on paper, but translating those into a system, right? Once you have an architecture, you map it to that architecture. We have to verify that we still have a speedup against the best possible gold standard classical algorithm, right? On the best classical computer or classical system you can think of. We have to be better than that as a quantum solution, right? That's when you provide value. You're better than the best possible gold standard classical system and solution. And so we started a team at Microsoft to really focus on the question of how do you take a quantum algorithm and then actually predict the cost on a real architecture or system, even if that system hasn't been built yet. What will that cost be? And I mention this because there's two avenues that I think are really, really exciting that have come from this work. The first is we've understood that, as I mentioned earlier, computational catalysis will be a true, practical, high-value application of quantum computers once we build the quantum computer to the size required, and that's the million qubits and beyond. We didn't have that understanding earlier. In fact, when you looked at the quantum algorithm for chemistry just 10 years ago, for example, guess how long it took to run on the quantum computer? And this was considered efficient from a computer science perspective. 24 billion years. It's not really practical. So we were able to take that algorithm and now it runs in the matter of a month for example, a ruthenium-based catalyst that would help us understand how to do carbon fixation, carbon capture, in a more ambient, efficient manner. So this is pretty exciting. So that's one avenue where learning about quantum algorithms has helped us understand what the true application of a quantum computing system might be and the cost, how far are we from getting there? What do we need to build? What do we need to develop to get there? On the other side, this other avenue is in the area of optimization. So as we've studied quantum devices and we've studied how they behave and we study quantum algorithms, we see that we can actually emulate some of that quantum mechanical behavior that we're taking advantage of in quantum computing classically. Now, while it doesn't get us all the speedups we would dream of on the quantum computer, it gets us, a good portion of the way there. And we can do it today, right? We can deploy it on classical systems. We can deploy it in Azure, for example, already today. And this is where I think there are applications to the military, applications to the Department of the Navy, where you're looking at, as I mentioned earlier, optimization problems where you're looking at scheduling, routing, logistics problems, risk minimization, anywhere where you have a hard optimization problem, a handful of constraints that you're dealing with, and you need to make a decision, you need to make a prediction or, find an optimal model or solution. And so to give a few examples where these commercial examples may carry over to similar applications in all of your domain, as an example, take some work we've done in, for example, traffic routing. So with Ford, we've worked on providing more optimized traffic routing through, say, a congested city, and we've been able to reduce the average commuter's time by around 8 minutes or so, right, across Seattle, which is pretty significant. Each way to work, I get to save 8 to 10 minutes of my day, and we can, for example, with JIJ and a customer of theirs, Toyota Susho, we've been able to minimize the time cars are waiting at a stoplight, at traffic lights. So do traffic light optimization. What does that do? That obviously minimizes the time you're waiting in your car at a traffic light, but it also helps with regard to sustainability, right? With carbon emissions. And there we've been able to reduce on average, the amount of time each car is waiting at the stoplight by about 20%. Which is very significant. So you can imagine how these applications may carry over to some applications in your domain. Another one is with Case Western Reserve University in the medical diagnostics space. We've been able to take these quantum-inspired optimization solutions and customize them in the case of pulse sequence optimization. When you have an MRI, there's a series of pulse sequences, right? If you've had an MRI, these loud sequences of pulses that occur, and it's very long, right? You're in the tube for a really long time. And we've been able to reduce that time, make those scans up to 4 times faster. And in turn, also, if you want to optimize for the image precision, we can make those images 30% better. And what does that mean? That means that now you have better throughput through the device, right? It means that a child may not have to be sedated before going into the MRI machine. It means that you can use that MRI machine that much more during the day, right? And have efficiency of the use of the equipment. On the image precision side, it means that you may be able to diagnose a therapeutic treatment working, for example, in the brain much earlier. Does chemotherapy work? Is it the right regime that I'm undergoing, right, for my healthcare direction? So, this is very powerful in the health industry. So those are a few examples. We've also used it in the optimization of materials. So with OTI Lumionics, we've been able to look at organic LED technology, so heads-up displays, for example, and help optimize the materials and the material selection that OTI Lumionics is doing for improving their OLED displays. So optimization, again, is very pervasive. Those are just a few of the many examples. Also energy grid optimization, et cetera. So I think these solutions we've developed for various enterprises are very applicable to this domain as well. And again, they can be deployed, customized today.
Thanks, Krista. Another question that came up in our chat was contributed by one of the folks in the audience, which is great. Keep that up. And maybe I'll send this one over to Bob. As a nation, where are things with regard to this technology? Is the U.S. Have some of the leading industry and academics? Is the U.S. trying to catch up? How's the rest of the world doing? There's a lot of discussion of great power competition in many different ways, and technology is certainly one of them. So maybe you could give us a few words on where we are with respect to the rest of the world.
Okay, thanks, Paul. Yeah, I think as sort of a preface, if we go back to the 1950s and 60s, when microelectronics was being developed, the U.S. led that field alone for decades. And it wasn't until the 1970s that many other nations began to see the promise being realized and wanted in. It's a very different time today with quantum computing. Other nations perceive what happened with microelectronics and the strategic advantage that the U.S. was able to gain. And even though I think the U.S. was probably first in and has pushed very hard, other nations are trying very hard to catch up and to exceed. China has stated publicly their intention to lead this field, and I think we have to take them at their word for that and realize that they're probably willing to use any means possible in order to get that advantage. And that's, I think, clear to us as a nation. It's also clear to us as U.S. industry that we realize that we are playing in a field where not only are we trying to be the best in the commercial space, but that we have as one of our adversary commercial partners a nation, a very large nation, and willing to do all kinds of things. So where are we today in the U.S.? I think the U.S. has been first to demonstrate almost all of the key advances in quantum computing. We are now at this point where we're beginning to go from pure research into applied research into development. And we know that this is something that's going to take increasing amounts of resources and devotion of time in order to accomplish successfully. And we know that other nations are going to pour it on hard, so that if we're going to win this, we're going to have to fight hard, and we're going to have to keep running and not look back as a nation. And that's traditionally a hard thing for the U.S. to do. But this is a field where we have significant competition worldwide. And we also have to realize that the U.S. does not have a monopoly on good ideas, that we have to continually scan the rest of the world, figure out who should we partner with as a nation in order to develop the field as rapidly as possible. And who should we be incredibly careful about talking to in order that we don't get our clock cleaned as a nation as well? Back to you, Paul.
Thanks, Bob. You know, in a similar vein, maybe I'll ask you this one, Charlie. You know, one of the folks in the audience asked about you know, with the excitement in this area. You know, in the past, the U.S. has had various challenge problems, various, you know, huge efforts in various directions. You know, obviously the moonshot was one, even DARPA Grand Challenge. You know, their autonomous vehicles program, much smaller scale, but you know, it was a real focus that shaped industry today. You know, one of our guests was asking, you know, is this you know, is this appropriate for something like that today? Is this something that might benefit from a big challenge problem? I think you're on mute, Charlie.
I want to just add a little bit to what Bob says before I answer your question, that this is really about talent, you know, being first to benefit from this technology and first to get there for economic and national security impact is about talent and focus, focusing on the right problems and having the right people both on your team in the nation and partnering. And the focusing on the right problems comes right back to knowing what to do, and it goes right back to talent. So, you know, if there's something senior leaders can do, it's help generate that talent. And when you look at going into building, it's not just about, you know, taking an online class and getting a bumper sticker saying I know about quantum computing. It's about mixed signal design, you know, semiconductor physics, software engineering, mechanical engineering. So I mean, real microwave engineering, real fundamental skills that will be valuable in many domains that will benefit the nation overall. You know, so those are the people we want to be generating here, who know enough about, we learn about quantum to be relevant in this new field, but could benefit everything. So getting back to the all of nation effort, you know, so we do have something called the National Quantum Initiative, you know, which I'm trying to coordinate in the White House. And the intention there was to, first off, get the government agencies working together to focus on the right problems. So even after 20 years of investment, it's not like we obviously know what to build. Like we need to build a rocket to go to the moon. You know, we're still trying to explore enough so that we don't miss out on the disruptive thing that could get us to where we need to be in 10 years or 20 years, right? So one of the things we did working with the community was ask, what are the big challenges? You know, what should the country be researching and developing to get to that next step? And we published that collectively as the Quantum Frontiers report. You can find that on quantum.gov, which sort of lists out in the different areas beyond just quantum computing. And here are the material science things we need to work on. Here's we need to find applications to justify further investment, because when you start to get into the billions and tens of billions, you know, of investment, you want to have some notion of how big a machine, like Krysta was talking about, would you need to do something useful, and are the applications big enough to justify how much? Because you're making decisions. You know, should we focus on fund this, or should we fund satellite development or other types of semiconductor physics? So it's a complicated question. We've taken a first step at organizing across the government. What are the hard problems for the government to invest in? And from those, we're building the sort of the mini grand challenges to justify that next step. But I would hope that at 5 years into the NQI, we'll be able to say, okay, we have a lot more confidence now that there's going to be an economic value here at this level. And that's going to justify the next phase of engineering and development and procurement of bigger machines to drive the economy forward. Thanks,
Charlie. You know, another one of the questions that came from the audience, maybe I'll ask this one to you, Krysta. You know, we've been talking a little bit abstractly about these quantum computing machines. You know, and I think at some level everybody has a reasonable picture in their head of what a conventional computer is, right? It's either a laptop or a desktop or, some supercomputer at, one of the DOE labs that you see pictures of but never go visit. For quantum computers, is there a fixed technology that it's based on? Is it, for example, in conventional computing, almost all of it is semiconductors, right? That Intel and others that, have fabs that work on it. Is it one fixed technology that really is going to drive the computing, or are there multiple technologies that are sort of still in the race, if you will? Maybe you could give us a quick picture of sort of what that looks like today.
Sure. Yeah. So it's very different than what we have classically right now, because we do not yet know which technology, or let me say which architecture, is going to reach the size, the requirements, achieve the constraints or overcome the constraints, right, required to reach the scale required to solve these problems we want to solve in chemistry, for example. So the jury's still out in that sense. There are several different technologies in the process of development across the industry, across the field, whether that be through government, academia, industry, right? So you see many different options in there. The options range from everything from, say, photonics to neutral atoms, spin qubits, ion trap systems, to very new types of physics involved. For example, what we're doing at Microsoft with topological qubits, and then you have superconducting qubits, which perhaps you might say are maybe the closest to what you might think of as what we have in our classical computer. But across these, they use each of them has their if you look at kind of the pros of the system and then the challenges of the system, right? Each of these options have different pros and challenges on the path to scaling up. So when you think about a quantum computer, it's important to look at a few dimensions as you think about which technology or which architecture I like to think of more specifically, right? Because it's also the architecture around. It's not just the qubit technology that matters here, right? We're talking about systems engineering, full integration across many layers, a lot of complexity that we have to bring together to make this whole machine work. So the underlying qubit technology is one piece of a very complex system that we need to make work. Some of these qubits have to run at cryogenic temperatures. Some of them can run at 4 Kelvin, some of them need millikelvin. So, one of the pieces of technology and the development we need to bring a quantum computer forward is, the understanding of cryogenics. We've heard a lot about materials, right? Some of these technologies use very exotic materials, some more standard materials. The system we're working on at Microsoft with topological qubits uses a semiconductor superconductor interface formed into a nanowire, and that and then that nanowire has to undergo a large magnetic field and be at cryogenic temperatures, right? And so you're really looking at these semiconductor superconductor interfaces that have to be, basically perfect, right? Perfectly atomically aligned. So we need these very high precision new types of materials development. We need to be able to measure and understand these materials. And this is true in some of these other technologies as well. In these photonic systems, you need new ability to generate photons on demand to be able to detect if they're still there. You need to set up, ability to send these photons across large distances and maintain entanglement, and right. So a lot of exciting technology development being done as we work on these different architectures. I think what's important to think about when you think about these architectures and you look at these systems, I like to think about it in terms of kind of 3 simple attributes or characteristics needed, right? You need a system that's going to be reliable. So often you'll hear about the error rate of a qubit or the fidelity of the qubit, right? So that underlying system, ultimately you have to build a system that's reliable. If your qubit's not as reliable as you need it to be, you can overlay it using more qubits and quantum error correction to make it a better system, right? So you need high reliability. When we talk about chemistry algorithms, material science algorithms, you have to make it through around 10 to the 12 to 10 to the 15 operations. So you need a system that's reliable to, each operation, 10 to the minus 12 or 10 to the minus 15, right? So that's pretty darn reliable. Then you need a system that's not going to be too large, but not too small either, because you have to fit a lot of control electronics onto these chips and onto these qubits. So qubits like to, we want qubits to entangle with each other, but we also want them isolated from the environment. And this is where it's kind of a push and pull scenario, right? If you isolate it really well from the environment, it doesn't want to entangle with its neighbors or the other qubits. So this is a trade-off. But so we need these reliable qubits. We need systems that aren't too big, aren't too small, so you can get control electronics on there. You need qubits that can entangle with each other, but also stay isolated from the environment. And then you also want to make sure that you can scale up, right? So then you're going to need many, many qubits in the system in order to achieve the algorithm. So you want to look at that systems integration, system size, and scaling up there. But it's an exciting time. And as Charlie mentioned, right, we need the talent that can develop all of these different pieces, right? You need to co-develop the hardware and the software. We need people that understand these device physics, understand semiconductor and superconductor physics, can build out the materials in order to realize these systems.
Thanks, Krista. Another question that came up, and maybe I'll send it over to you, Bob. I know that your earlier work on the Defense Science Board, often looks at big picture ideas and things like this. One question that came in is how can senior leaders influence this research, adoption, integration of things that we're talking about? Is it just learning more about quantum computing? Is it something more? Maybe you could talk about how the senior leaders can have an influence here on the trajectory.
Sure. I think within this is a field which is nascent. So much like in earlier eras where we had space come up as a new means of affecting a strategic advantage, and we needed people to become skilled in understanding all of the nuances of how we would utilize space or radar or conventional compute. In the same way, we're facing the task now of growing a cadre of people within the military that will have a grasp of the potential, the state of the art and the potential that could be within quantum computing, and begin to then take that and apply it to the problem spaces that they have deep knowledge of. Because the technologists themselves, we're all in love with the technologies that we develop. We think about them morning, noon, and night, but we are not deep thinkers in the strategic domains that are the specialty of the DoD. So having that group of people in DoD that can act as the interface into this nascent technology, I think is incredibly important. As Christa pointed out earlier, two things are at play here. Number one, when we finally have these large machines that can successfully solve large problems, the way we will architect algorithms will be fundamentally different. And there too, if you go back to the 1950s and 1960s, when information technology began to hold sway, business changed fundamentally and quickly. And in the same way, we should fully expect that in signal processing, in optimization of resources, in gaining strategic advantage under a rapidly changing environment, that quantum computing will enable us to do things in the future that we are unable to do today and can't fully anticipate today. And having the rising leadership able to comprehend the art of the possible there is something that will, getting back to the talent that Charlie spoke about, enable the US to take the lead and to run with it. This is a game where there's only first. And everybody else is a loser. So it is imperative that we have the people who can think within this space and understand how it can be applied to maximum effect. Back to you, Paul.
Thanks, Bob. I want to thank everybody so far. We got another hour to go, but just as a time check, thanks everybody for sending in questions. I think they've been great, and I encourage folks to keep that up. One question, maybe I'll send this over to you, Charlie. One of the things that has come up recently that we all associate with conventional computing, classical computing, is the internet, and the quantum internet has showed up in the headlines a bit lately. What the heck is this? What is this even possible? Maybe you could answer that one. Over.
All right, the quantum internet. Yes, we love this topic because it's whatever you imagine. Well, let me start with the basics. If you have a quantum computer, and you want to make it bigger, you want to double the size of the quantum computer, you have to make it all quantum. Like, it has to have a quantum interconnect, meaning if I have two half-size quantum computers and I want to connect them to make a bigger one, I need to send quantum information fast enough between them to enable the computation. Otherwise, you just have two smaller computers. So it's a bit different from classical computing. But we do know that in the long term, should we want to enable bigger computations, we would like to network either quantum computers that are in the same room or same building together to allow for bigger computations, or potentially ones farther afield from each other. But for computation, you don't need, as Krysta was saying, you don't need to be able to run your code on a quantum computer. You don't need a quantum internet. You can just use the internet we have today to dial into Microsoft Azure or the IBM cloud or whatever cloud has a quantum computer, and run your code for the quantum computer on that through the classical internet, through a classical terminal, right? So that's the first thing to know. So in the long term, we'd like a quantum interconnect to make bigger quantum computers, but we don't need quantum internet for everything. We can use the classical internet for most things. It's also been thought that you could connect sensors together, quantum sensors, via some kind of quantum internet, quantum interconnect, to make a better sensors. That's a little bit more speculative. We don't know the benefit versus cost ratio for those, but it does motivate the field. Now, we do know a lot of other things, though. So I mentioned cryptography early on. So a quantum computer, if big enough, can crack public key cryptography. One of the first proposals for quantum application is so-called quantum key distribution, or using quantum states to create secure channels. Now, so that there's nothing wrong about that proposal. It works, but there's another way to do it. There's so-called post-quantum cryptography, where you can use classical codes, the codes we use every day, just on classical computers, to create encryption that's impervious to quantum attack. And that may very well be the more economical, better way to actually protect ourselves from future quantum computers. So what I'm trying to get at here in this complicated topic is there's a difference between connecting quantum computers and quantum devices versus using a quantum internet, which may motivate a quantum internet, versus making a quantum internet to do secure communications. The latter is probably not where we're going to go. The former, we're still trying to understand, what are the key components needed and when we would need such a thing. So it's much more of a research topic than, for example, quantum computing is, where people are really trying to build them and get to that first application space. I hope that helps.
Yeah, no, that was it was probably the best description of in response to the question I've heard. It was very helpful. I also want to point to our audience members that the NSA has recently put out some good white papers on these topics, and so if that piqued your interest, there you can just search NSA quantum communication, NSA QKD. Those are good terms to look for, and they've talked specifically about this second application that Charlie talked about, the sharing keys, and why from the the punchline of that white paper by NSA that you could just look up right now in your side window, is that there are some major flaws to it, and that they need to be satisfied in order for NSA to certify them. But yeah, certainly when it comes to understanding how quantum information is passed between computers, this is a really interesting application that I know that the many around the DoD, including Naval Research Lab and Air Force Research Lab, are trying to understand and trying to understand where the applications will be. So we talked a little bit about the role of quantum computers in cybersecurity, and there's a big question that is there. We talked already about how there's this threat of big machines breaking codes, and that many folks in the U.S. government, including NIST, including DoD-CIO, are marching down the path of updating codes to protect against that. And so I think that's important to keep in mind and think about as that, which frankly is one way in which quantum computing is having an impact today, is that the fact that there are new major standards being developed for public key encryption is specifically to address this threat. Talks to both the potential of the technology and how serious people take these changes. And so maybe I'll ask a question about sort of recent advances. Maybe I'll shuttle this one over to Bob. What are some of the very recent advances in quantum computing that you're particularly excited about? Maybe in the last year or so that you've been particularly excited about and you think hold real promise.
Sure. So again, just to sort of put it on the grand scale, the machines that we're building today in IBM are not ones that are capable of solving problems that will have utility, but are machines along an incremental path that would achieve that. And historically, the machines suffered from many forms of degradation, so that the quantum coherence would be lost in the qubits over time. And a lot of work has gone into finding ways in which we can extend the time over which a qubit will be coherent. That work has gone on for the better part of 10 years. And what we're finding now is actually that the next level up, the application of waveforms and the details about how you design the qubits can have an enormously powerful effect on the fidelity of qubits that you can achieve. And I think that's a frontier that we're just beginning to push on today in the technology. And it allows us to build machines that are higher fidelity, but also more coherent, so that in terms of where we are, to use an airplane analogy, the machines we're building today are gliders. I can get a machine into a coherent state, I can start a computation, and it will slowly glide and lose altitude. And when it's hit the ground, I can't do any more computation. I've lost quantum coherence. And what we're looking at doing in the near term is making a little better gliders that can glide farther so that I can do longer calculations. Ultimately, these advances get us to enough fidelity and enough coherence that I can begin to layer on other forms of error correction as well. And some of those pieces of error correction are the classical error corrections that have been discussed in the field. And increasingly, I think there's compiler optimizations that are being discovered that can simplify the way in which we would actually run on real hardware. Those advances, I think, over the next several years will have tremendous impact, because the amount of entanglement, how I utilize it, and how I can take different domains of entanglement and have them work together effectively, I think are just beginning to be understood in the nuances that we can apply to them. And I think those areas over the next 2-3 years will have tremendous impact in this field. Back to you, Paul.
Thanks, Bob. You know, one question that has come from an audience member, and I'll ask this one to you, Charlie. You know, internationally, how do our allies view quantum computing? Is there interest there? Is there investment there from, you know, traditional Five Eyes partners, from others around the world?
Yeah, yeah, I'm still unmuted. There's a lot of interest all over the world in quantum computing. So I think as Bob phrased it pretty well, that nobody wants to miss the next big technological revolution. And, you know, although we don't know the implications of quantum information science fully yet, you know, what it does is, you know, drastically change our foundation of information technology. So the assumption is it's going to have big effects one way or another. And if you look at any other country, whether it be the EU or individual nations in the EU, China, India, Canada, Australia, almost every major country who does science and technology investments has something like a national quantum initiative or a big initiative around quantum information technology. In addition to all the local companies and VCs investing in it in the commercial space. So there's definitely worldwide interest in investment, and so it's in some sense a very different world than it was 50 years ago. Everybody's trying to be the leader here, and I think our perspective in the White House is it's much better to work fast, to move faster together than to try to compete with each other. So if we can find like-minded nations and work together with our allies and partners, that's better for everybody. And it not only helps move the technology forward so you don't waste time going down the wrong track, because it's very diverse technology at this moment. Right? We don't know the right thing to do, right thing to invest in. If we can do that, we can move faster, but we can also agree on, you know, commonplace rules, scientific integrity, intellectual property protection that will benefit all our investments collectively. So that's really our goal, but this is definitely a worldwide endeavor.
Thanks, Charlie. Christa, I asked a question to Bob a moment ago about you know, recent developments that he's excited about. I'd be interested to hear your view. You know, what are some of the recent things that you're particularly excited about?
Yeah, I mentioned some of them in passing in some of the responses to the previous questions. Let me call those out more explicitly. The work I mentioned on carbon fixation. So when we think about computational catalysis, that is very new work. Members of my team and then also colleagues worldwide, speaking of working with others around the world, working with scientists at ETH Zurich, we were able to develop that application, that algorithm that will eventually run on a scaled industrial quantum machine in a collaboration. And what we were able to show is that there is an efficient quantum algorithm to enable studying carbon fixation on a quantum computer, which in turn will enable us to understand how to design a catalyst that will enable an efficient reaction, right, for carbon capture. So the whole goal there is, right, you take carbon dioxide, you interact it with a catalyst that causes a reaction, and then, for example, methanol comes out. But what we want is we know catalysts exist to help with this process, but these catalysts, we want them to be conserved in the sense that we want that catalyst to be able to then repeat that process, not be destroyed in that process, enable an efficient process. And we want that catalyst to, once it does it with one carbon dioxide molecule, right, move on to the next and keep going. And so we want that efficient process. We want that to be able to, you know, to be easily deployed in ambient environments. And that's the type of problem we can study on a quantum computer. Studying those quantum correlations that occur in that reaction with that catalyst on supercomputers, on your high performance computers, you know, it's intractable. Right, it's far too long. It's lifetime of the universe timescales, right, to get the accuracy you need and that level of understanding you need to do that design classically. So this advance, right, this ability to understand this type of process on a quantum computer with a quantum algorithm, I think is a huge step forward for our field, for the industry, right, that there's the promise that this quantum machine can do that. I think in addition, the other areas I'm very excited about are also point to that direction, like starting to understand what do we need in a quantum machine to perform such an application, right? So now that we have an understanding of that application, we can in turn now start to co-design that system. We understand that I mentioned the size of the system matters, right? You don't want to try to keep a skyscraper coherent. If our quantum computer, when you scale it up to the numbers of qubits required for that algorithm, is the size of a skyscraper, good luck trying to keep that whole system coherent, right? So you really want a quantum computer that's going to be, more compact. Maybe it could be the size of a room, but probably not the size of a skyscraper. And ideally, it might sit on a single wafer or be kind of a single module. So that's one consideration we've learned through this work. Another axis to think about is the operation speed. So I think one thing we overlook is once we have a quantum error corrected computer, once we're trying to make that architecture reliable, what's the logical clock rate? What's the clock rate of the quantum computer at that algorithm level? It's around 10 microseconds in most cases. That is not very fast compared to our classical machines, right? Classical computers operate at sub-nanosecond timescales at that, for clock rates, right? So you're competing with a clock rate that's very fast classically, but slow quantumly. That's okay when you have so many fewer operations required in that quantum algorithm, right? You have exponentially fewer operations, so that's possible, but we have to check that for a whole variety of applications. Now that we have this understanding of what the difference between the logical clock rates are, we can then in turn look at an architecture and we can understand, is the underlying gate operation of that architecture going to be fast enough to enable this application to run in about a month? If it takes the quantum application, like I said earlier, 24 billion years, or even arguably 1 year, right? That's probably too slow to be practical. So I think what's really exciting, what I'm getting to is what I find really exciting right now in our field is we are understanding the applications and we're co-designing, we're taking that understanding and we're using it to build a better architecture and to unlock an architecture that's going to enable scaling to running those applications. I think that's a huge step forward, a huge level of insight for our field and our community that's going to enable us to make this progress and continue our momentum forward towards scale.
Thanks, Krista. I'll share something that I've had some discussions with scientists at the Naval Research Lab, and along the same lines as some of the chemistry problems that Microsoft is looking at, some of the things that excite them the most is understanding corrosion better. When we started talking about this, I did a quick search, and the Government Accountability Office has written several reports upon how much the Navy spends on handling corrosion every year, and it's in the billions. And so, I imagine that if NRL's research on this and using quantum computers led to better alloys or better processing or better coatings, this may very well pay for itself in a few years just for the Navy, right? And so and while it's still an open problem for them whether or not that they can tackle the corrosion problem with a quantum computer. I think it speaks to the fact that people really are looking at some really big problems and that they're coming from all over the place, and really understanding how to use these new machines is a real exciting endeavor for a lot of folks. I'm going to ask a sort of a simpler question. Maybe I'll throw it to Bob. If somebody has software running on a conventional machine, can they just port it over to a quantum machine and will it run faster? How does that work? Or do new things need to be developed? Over.
Okay. A very good question, and one that frequently comes up. So in general, a quantum computer is a coprocessor, an accelerator, and it's an accelerator for certain classes of problems, but not for everything. So you would not want to run your favorite piece of C code on a quantum computer because, as Krista said, it runs much slower, and it would be a sad thing to watch. But quantum computers have the flip side capability that because of this quantum property of entanglement and the fact that it can effectively by entangling arrays of qubits, do mathematics at a rate which is unprecedented by any other measure that man knows, can solve some classes of problems very, very quickly. And this is what Peter Svore did when he was looking at the factoring of numbers, to take a good advantage of where the quantum computer can solve things better than the classical machine can. So we wouldn't really want to just port code over, but in fact we do want to make the machines accessible through things like Python or R, or choose your favorite language, and whatever your favorite language is the best language. I have no argument with that. That's a religious debate that I'm going to steer clear of. But it needs to be able to connect into it, and it needs to appear as modules or libraries or an accessible alternative to whatever you're doing today. And in all likelihood, whatever algorithm you're implementing today would need to change in some fundamental ways to take advantage of the quantum computer, much as algorithms changed when computers were applied to everything from manufacturing to assigning airline seats. The way you do things changed when you had a conventional computer. The way we'll do things in classes of problems will change when the quantum computer comes of age. So I'll use conventional languages, but I'll use them to solve problems in new ways, some of which will still run on a conventional computer, and then hand off certain problems that the quantum computer can do better over to the quantum accelerator, take that answer back, and continue to process with it. In terms of then, how does this plug into the network? So this is why it is important to get in the game early in terms of understanding the algorithms, because if you wait until the quantum computer is ready to begin to envision how you would change your business process to take good advantage of it, it's too late. Other people will have been out ahead of you, and now you're playing a tremendous game of catch up. And this is the tale of the 1960s in the commercial landscape, that many companies felt that computers were a fad that would pass, and that you would always keep bookkeepers around and big ledger books because, gosh, that makes just good sense. And you'd use buck sheets in the manufacturing line because that made good sense for 100 years. Why mess with that? And in fact, within months, in many cases, such advantage was gained through the use of information technology that the fundamental commercial field changed overnight and declared winners and losers. And there was no time for catch up. The people that had chosen not to stay with the state of the art literally were left behind. And I think that there's the risk here that something very similar can happen as these machines mature, that the people who have invested the time, the people time to deeply understand how the machine is maturing and what it's capable of, and figuring out how the algorithms should change to take advantage of it, will be the first to take advantage of it, to get the profit out of that, both in the commercial space and in the strategic space for the nation. And it is imperative for us to be ready and to stand up to that challenge. Back to you.
Thanks. This next question was pretty interesting, and I'm not sure that there is a maybe I've missed it, but I think this is still something under development across the country, and so I'd like to do this round robin style, like maybe first go to Charlie and then Christa and then Bob. First for a point of view for each of you is one of the folks in the audience asked about how does Naval Postgraduate School after today's discussion, if there's interest, and I imagine there will be, to stay abreast of the latest results that are happening, to get more engaged. Are there ways that are already established to do this, to stay abreast and participate in what's happening, or are there still things underway, under development, or is more needed? So maybe I'll give it to you, Charlie, for to talk about that, and then maybe ask Krysta and Bob. So go ahead, Charlie.
Well, you could probably invite one of the speakers once a year to come give them an update. That would be a good way. I mean, you can also go to quantum.gov. That's the website we launched in the coordination office to disseminate what's going on in the government. And one of the things we have in the subcommittee that me and Paul are on is an end user working group, and we hope to work towards some kind of, I think for users, for agencies that are like users like NIH or others, or potentially the Navy Postgraduate School or Navy, people who want to be users of this technology, not necessarily funders of it, to give them an update on what's going on, what's truth from fiction. But if you just do a Google search, there's a lot of stuff out there. There's a lot of newsletters and stuff. Some you need to take a kind of an average and divide by 10 in terms of the hype factor, but you can at least get a sense of what's going on. I think that's a good way. There's also a Quantum Industry Consortium, QEDC, which you consider following. They're, I think, starting to put out reports and at least their analysis, the industry analysis of what's going on. So those are a few ways, but I would find a few trusted people who've been around this field a lot and ask them, once a year. So what's it going? And are there any applications we should know about? And talk to Paul Lopata, who's has a job similar to that in the DoD.
Thank you for the plug, Charlie. I will hand it over to Christa. Are there ways that you see of organizations getting engaged to learn more and get involved?
Yeah, so one way to get engaged, in addition to what Charlie just outlined, is through working with with industry and development of applications. We have a program called the Enterprise Acceleration Program and something called the Microsoft Quantum Network. And with our EAP, Enterprise Acceleration Program, which isn't just limited to enterprise, by the way, that program is the program in which we have worked with, for example, Case Western Reserve University, Ford, and others to customize solutions in the quantum space, whether that's quantum-inspired optimization solutions or full quantum solutions for future deployment. We bring our quantum algorithm experts to the table with domain experts coming from the respective organization we're working with, and together around the table we develop and customize solutions to either deploy today or to deploy on a future quantum machine when ready. And so this really enables early conversation, early innovation. It enables being a first mover, to have to be a first mover, to have that first mover advantage in the space and have quantum impact today. So I think bringing problems forward through the Enterprise Acceleration Program is a fantastic way to begin innovating on those solutions. In addition, I think the other important piece I would say is that as a user, if you want to be an end user of the technology, not necessarily innovator within the stack, then I do think it's very important. Not only we talk about developing curriculum for students around computer programming and knowing how to program, right? Being computer literate. I think the time is now to be quantum literate, to understand what quantum applications look like, to try quantum programming. If you're in the software and development space and you're engaging in machine learning and AI techniques, right? GPU programming. There's many different paradigms people are using today for programming. I think it's important to add the quantum paradigm to your list, since that is emerging and will be a key paradigm, a key model as we go forward. So again, try Azure Quantum. Go jump in right now. Open your browser, write a quantum program. You can try Teleport. Do your quantum hello world, and you'll already be on your path forward.
Thanks, Krysta. And Bob, same question. What are ways that folks could get engaged? Either learning more or over time to staying abreast.
Sure. So I think IBM, like Microsoft and others, has been pursuing the outreach part of quantum for some time. A group of us back in 2015 walked into our VP's office and said, we'd like to put a quantum computer on the web because no one's done it, and we think that people would be interested in trying it. And our VP, Dario, turned to us and said, well, okay, how many people would come and use a quantum computer if we put one on the web? And we said, well, by our analysis, there were about 1,000 quantum information scientists on the planet, and about half of them like us and about half of them don't like us. So we think about 500 people would come and use our quantum computer. So he said, well, okay, well, we can go try that. And in May 4th, 2016, we put it on the web. And about a day later, we passed 20,000 people using the machine. That the appetite for using real hardware and trying things out was way beyond our wildest dreams. And that has continued to this day. So at the moment within IBM, we have 20 quantum computers that we make available either free on the web or to our partners within the IBM equivalent of the Microsoft outreach for commercial space and for government space. And those machines allow people to program, to observe the results of the program and see how the machines are changing over time. And there is enough evolutionary change in these machines that every one of them, as we continue to evolve, shows new things and shows the differences, shows the warts as well as the gains. And that I think is one way of gauging what is the rate and pace of change in the fundamental technology. That's useful. More importantly, I think getting back to how might you use it, you can begin to look at which slivers of an algorithm might be appropriate for acceleration on a quantum computer, and which problems have algorithms which don't require the biggest, greatest, strongest, fastest quantum computer ever, but in fact will require the weeniest, slowest, worst quantum computer that could still give us an advantage, because that's our goal. We want to build the just good enough quantum computer as soon as we possibly can. And I think I heard in a discussion with Christa some years ago during the DSB call, I think Christa was saying that one of her goals was that whoever built the first somewhat usable quantum computer that could do materials analysis, let's build the perfect materials for a better quantum computer out of that one. And I think that kind of bootstrapping might well be a path forward for us in the field. So those things exist. There's I think there are over 100 companies interested today in understanding what quantum computing could mean for them in the future. Not that they want to make them, not that they want to understand how to build a qubit, but they want to understand how to utilize it further on. And I think that list will grow every day. I think in the same way, there's an appetite within the military to grow the young officers to be quantum literate, to understand that this, like other technological advances in the past, will allow us to gain strategic advantage in ways that we can't fully foresee today. And that those are good investments for us to make in the near term. Over to you.
Yeah, thanks. No, that's great. And I'm also going to plug some work that's going on, elsewhere in the Navy. There's folks, as I mentioned earlier, at Naval Research Lab who are working on quantum computing, understanding algorithms, understanding qubits, and they've established a center within the Navy at the Naval Research Lab, and there are paths there for some serious expertise and to develop even tighter relationships there. And so those are all great ways to both update your knowledge as this develops and get more engaged. Charlie, you mentioned this question of hype within the technology. And, it's something that, I certainly battle against at times, that I'll talk to folks and they'll say, oh, we got to, put in a huge order for a, major quantum computer to be delivered next year, we're going to start calculating things and, solving important problems and things like this. And, I love the enthusiasm, but, sometimes it gets, sort of stoked outside of the bounds of reality. How does one, navigate this situation where there is tremendous excitement, tremendous, real possibilities here, but at the same time, you hear folks talking about, how it's going to do all sorts of things that it really, frankly, never will. So how does one navigate the hype versus reality here? Charlie?
It's challenging because, this can be a complicated field, and you can quickly use words that overwhelm you. And even I, as a quantum physicist for 20 years, when hit with the onslaught of a new company claiming this or that, can get swayed before you say, well, wait a second, that seems kind of impossible. So I think, making friends with people who are experts in this field, finding the centers of excellence within the government, not necessarily just within the Navy, but within the broader DoD and the IC and the government, and having regular conversations with them before you go into major decision points, I think is incredibly valuable, because they can say, oh, we've been funding that group for 10 years, nothing's happened, or they can say, oh yeah, that's going to work, but it's going to take 5 years, 10 years from now, think of it in this timeline. It's really important that you understand the timelines here, because this is still very much, although all of us on this call are true believers, we've devoted our careers to this. This is measured in decades, right? 20 years looking back, 20 years looking forward. We're hoping to find applications as soon as we can. But you have to consider this as an investment in the future, right? That it's going to be relevant. We need to understand it, but it's not a. I always think back to this one conference we had in the UK. I don't know if you were there, Paul, but the question you use a quantum computer for, and somebody got up there and listed every hard problem known to man. Cancer, this, that. You can list every hard problem. That's probably not the, this is not the magic machine, right? It's a new technology with specific use cases that you have to understand. You have to understand the timelines. So you should enter everything with optimism, but caution in terms of when reality will actually hit.
Thanks, Charlie. No, that's good. I think we've just got a few more minutes left, and so I want to give each of the panelists an opportunity to to talk about the future, to talk about say the next 5 years and even beyond, if you'd like. What are I guess my big question is, what are some of the things you're looking forward to, going forward. And I'll do it in reverse order to how we did the introduction. So I'll go with Christa, and then Bob, and then Charlie. So looking ahead, what are some of the things you're looking forward to, Christa, in quantum computing? Over.
Well, there's no shortage of things I could put on this list, but I know we have limited time. I think, obviously, I think. Hopefully you all feel my passion for the application space and making those applications a reality. So, what I'm most looking, the moment we run, for example, a catalysis problem on a quantum machine is just going to be historical. I mean, no doubt it will bring tears to my eyes. I will be crying when I see that result come out of that machine. So, I can't say exactly when that's going to happen, but it's going to happen, and I cannot wait for that moment. Along the path to that moment, I am very much looking forward to really inspiring a generation of people coming together around that moment. I'm looking forward to seeing increased diversity in our field, in the roles, in the people coming together around the table to talk about applications, in the opportunities ahead. I'm excited about integrating a system, right? A system that will have the reliability, the speed, the size needed in the early, even if it's an early system, knowing that we've hit these different benchmarks needed to begin that scaling up process. So I'm just incredibly thrilled for that moment ahead. I'm also excited about the eureka moments in the path during that time. I feel that while we know a lot, as we work to innovate and integrate, we're going to discover and learn a lot more. And I think the incorporations of those, those learnings along the way, that continuous learning process is so exciting. So I'm looking forward to what we learn as we actually, co-develop that system in its entirety, as we think about the applications, understand them better, and bring it back to that co-design environment. I feel like we're going to be writing just textbook after textbook after textbook in the next several years, and that's truly thrilling.
Great, thanks, Krista. I think I promised it was to be Bob next. So what are some of the things you're looking for in the next 5 years and going forward?
Sure. So let me break it into a 5 and then 10 plus years. So over the last 10 to 15 years, I think we've done a lot of work in the fundamental science and trying to determine whether a quantum computer is even a possibility. And I think from sort of a theoretical experimental proof point, we know now that we can build qubits that work well enough that I can do simple things with them, and that I can keep them improving on a fairly constant rate. And more now, there are elements of the problem, how I drive them, how I error correct them, how I make bigger and bigger cryostats and connect those cryostats in such a way that I can grow the power of the machine, that not only have still remaining scientific problems to solve, but are increasingly falling in the domain of engineering. And the engineering domain has differences from a purely scientific one. And when a field enters that engineering domain, then large teams of people can work together to solve problems much more rapidly than one might naively think. And I've seen this several times in my career at IBM, starting in flat panel displays back in the 1980s. We had spent about 10 years on internal development and several $1 billion getting to that first production line. And I remember showing that early display to our new CEO at the time. And it was a wonderful time because he had never seen anything like that before in his life, and realized that the world that he knew had just been fundamentally changed, and that forever after, flat panel displays would be the way that people looked at information. In the same way in microelectronics, within IBM, we spent over 10 years and many billions of dollars bringing a copper wire to the back end of a chip. Seems mundane. It was, but there were huge engineering challenges that we had to overcome. And some of it was scientific, that we needed to understand the details of interfaces and how diffusion occurred. And some of it was just trying it 1,000 different ways until you figured out how to make it work. And there are elements of quantum computing that are entering that engineering domain. And that's what makes the next 5 years extraordinarily interesting, because we will make progress on some of these things to allow us to build machines that get closer and closer and closer to the point of utility. And that will help us in the near term to not only learn about the machines and make the intuitive leaps that we don't know yet, the pieces of information we don't yet know, in an agile way, but also allow us to experiment with the algorithms. And between 5 and 10 years, I think we're building machines that get closer and closer to that point where we toggle over into solving problems that really, truly matter. So this is something not in the far distant future. This is something within this decade that will change the way humans think, that will change the way we think about what is possible. Not in everything. It will not cure cancer, give us infinite energy, whatever you want. But it will, properly applied, it will give us tremendous advantage, and both commercially and as a nation. And taking advantage of that fully is something that is ours to hold and to grasp and run with. And I think it is the moment for us as a nation to act coherently and cohesively. Back to you.
Thanks, Bob. Just in another minute or two, Charlie. What are you looking forward to?
Really quick, so I'll just
years?
say there was a question in the chat about education. I wanted to mention the Q12 education.org partnership, which IBM, Microsoft, and many other companies are part of. Its intention is to bring this to high school students and below, and bring some of this opportunity to them. So please check that out. In terms of what I'm excited about, I'm a technologist, so I'm excited about building a quantum computer that nobody thought was possible. So first and foremost, but speaking for the government, I'd say I'm most excited about getting to this point where there are too many amazing job applicants for me to hire for each job position, and not just software, but RF engineers, microwave engineers, chip designers. We need to get to that point for the country. And if we get to that point, I think it's going to benefit not just quantum, but a lot of different areas, including military's goals. So I hope we can work on that together. That would be a big win for everyone.
Thanks, Charlie. And I want to take a moment as we're wrapping up to thank all the panelists. This was a real pleasure for me today. Hopefully, we got a lot of folks who stuck around. We've certainly got a lot of interest in the question and answer. I want to thank everybody who submitted their questions. Probably about 2/3, 3/4 of the questions we asked today came from the audience, which I thought was fantastic. And then finally, thank you, Sheila, for hosting us, and I'll hand it back over to you.
Thanks, Paul. This has been a really illuminating discussion, and I'm glad you all kept it at the level of a conversation that most of us can understand without getting into superposition and coherence and error correction codes and stuff like that. So for that, I applaud you all. But the challenge for us now is to really figure out how to harness the horsepower you all represent into programs at NPS and at other educational institutions within the DoD. So we will be coming back to you. Please help us and be prepared. This is a request to take us forward. I mean, this is an arena that's going to come forward in stops and lurch forward in bits and pieces. So we need to keep abreast of everything that's going on in the field. So thank you again, Bob, Charlie, and Christa, and of course, Paul and Claire in the background, and our support team, our audience. This has been exciting for me personally. And let me now pass it on to Colonel Randy Pugh. Randy?
Thanks, Sheila. And on behalf of Admiral Rondeau and the rest of us here at the Naval Postgraduate School, thanks to the panelists and to the moderator. As Sheila said, I appreciate your time explaining something that's so inherently complex in a way that's understandable, what it is, what it isn't, but most importantly, I think, is why we should and must care about it, all the way down to the deck plate level. So thanks also to our participants for your time and for your questions. And I just mentioned that our next emerging technology series is going to be on intelligent autonomous systems, robots and drones, and that will be coming up in May. And we look forward to another great panel. It'll be hard to top this one, as well as participation from our senior leaders and the rest of our audiences. So with that, we will say thank you and have a great rest of your day.